Good morning everyone, I'm Kerr. I work at the Science Media Centre and in collaboration with Te Papa and the University of Adelaide, I'm pleased to be introducing Professor Alan Cooper, who has a publication coming out in Science tomorrow morning which reveals some interesting twists in the evolution of what is probably New Zealand's most iconic bird, the kiwi. And we also have Alan Tennyson, who is curator of vertebrates here at Te Papa, and he'll be on hand to answer any questions and show some of the specimens involved in the research.
Thank you, and thanks to you all for coming at fairly short notice. What I'm going to do is just give about 12 to, I think it is, slides for about a quarter of an hour, just to give the background to the story, and then take any questions that I haven't covered, and I'm going to try and keep it as clear as possible. We've got this paper coming out tomorrow, which we're very pleased with, myself as a New Zealander particularly. And I guess, why is the work so exciting? Well, the rat-eyed birds and the evolutionary history of the rat-eyes and the kiwi have just been a question for 150 years or so. It's been puzzling scientists. The rat-eyes are this large group of large flightless birds found across the southern hemisphere. Things like the emu, the ostrich, and of course the kiwi. And they're separated from all the other birds that are alive on the basis of their palate, the beak effectively, and the skull. And they have a very primitive structure, hence their technical name is Paleognathus, which is, it means old-jawed, and that separates them from every other bird around the world. Now, evolutionary scientists have been puzzled by these birds. Why were they giant? Why were they flightless? Why did they only turn up in the southern hemisphere? And why do they look so bizarre? Ever since the first explorers started encountering them. And so, of course, in New Zealand you had things like moa being found in swamps as farming started to develop. And Richard Owen, very famous anatomist, one of the adversaries for Darwin, for the theory of evolution and Darwin, famously predicted that a moa, which he's standing next to there, would exist based on the small fragment of femur he was sent from New Zealand, where someone said it looked pretty much like a cow. He was able to accurately guess that this must have existed. Now, the rat-eyes are found on all the southern continents, and they generally were thought to believe to be in those places because they had once existed across Gondwana, which was the southern supercontinent here, which broke apart about 130 to 50 million years ago. And it looks, if I can get it to play, something like this, just looking at the continents coming apart. This is South America here, Africa, here's India, there's Madagascar, Australia, and this is what's going to become New Zealand, this kind of mess over here on the right. As these continents come apart during this period of time, the idea was these archaic primitive birds that were on Gondwana were separated and became different species just by being on those land masses. That's how they came to be in those spots. Now, about a long time ago, with bad hairstyles in 1994, I was doing a PhD up at Victoria, and you might recognise the bone in the background there, is this one here in fact. I was studying the rat-eyes, and my work was to use ancient DNA to retrieve material from the two extinct species, particularly the moa was the one that I was working on. I tried the elephant bird, and at the time I couldn't get it to work. This is one of the moa specimens that I was studying. And what I was trying to do was to get DNA material from these old bones to compare them to the living rat-eyed birds found around the rest of the world. And what I did was sequence a thing called the mitochondrial DNA. Mitochondria are these small organelles that survive in our cells and produce energy. That's how we get energy. And they've got their own little genomes. And what we did was to sequence the DNA from moa, and we got a tiny fragment from the elephant bird, but not enough to really be useful. Now the problem was, when we compared the DNA from the moa to all the other birds, we ended up with an incredibly damaging result, which was that the moa and the kiwi were not closely related. This is a family tree, if you like, showing the extent of relatedness between the different birds. So back when I did my PhD, we expected the moa and kiwi, both isolated on New Zealand being isolated for 80 to 60 million years, we expect them to be each other's closest relatives. The problem was the kiwi came out next to the emu and the cassowary from Australia. And so basically my PhD was showing that our national bird was an Australian, which at the time was incredibly unpopular. There was a huge media outcry and a lot of national angst at the time. Now, it's taken me 20 years to fix the picture, for which I'm obviously very apologetic. But what we have managed to do is to get the last remaining bird from the whole ratite family tree, this guy, the elephant bird. We finally got the DNA out of that. The elephant bird was the largest bird that we know, effectively. It's about 3 meters in height and 275 kilos in weight. It even put the moa to shame. There are the 4 recognised taxa at the time, with a life-sized Madagascar for comparison. Unfortunately, very few intact skeletons and not many bones are known from Madagascar. A lot of the material was not in optimal condition. This is what we think they look like, wandering around a spiny forest of Madagascar. Now, I've searched all over the world. I went to every museum that I could find that had Abiornis bones. There's probably about 15, 20 in the world. I've tried extracting DNA from bones all over the world. In the end, couldn't get any of them to work, and I was getting quite frustrated. Finally, recent advances in genomics technology enabled me to go back to the DNA we got from these original specimens in 1994 and retrieve DNA. So we use techniques which fish out the tiny fragments of authentic elephant bird DNA that are left, and in so doing we were able to reconstruct the ratite evolutionary history with the elephant birds involved, and found that now the kiwi is still closely related to the emu and cassowary. Here they are there, but by far its closest relative was in fact the Madagascar elephant bird, which is about as bizarre a finding as we could get. If I had to guess of all the ratite birds, which one the Madagascar elephant bird was going to be closely related to, the kiwi would have been the last by a mile, actually, not even a close second. It is bizarre. It looks nothing like it. It's on the other side of the world. I mean, here's Madagascar, here's New Zealand with our kiwi. They've never been connected directly by land. You have to go through India and then Australia and then Antarctica to get to New Zealand. Clearly, they did not do this by continental movement. There's no way you're going to get a direct connection between those two. They're as far apart as you can get. Morphologically, completely dissimilar. No one has ever suggested the kiwi and elephant bird might be closely related. So they've got to have flown, clearly, and work recently on the moa has suggested again that flight was involved in the ratite group. That's the only way you're going to get across that area. And furthermore, we can actually test this. We can say, okay, if it was continental movement, this is the relationship of the ratite birds you would have got. And what we've done is just group the continents by colour as they separate. So Africa comes off first. That's the dark one. So that's the ostrich and the Madagascar elephant bird. Then the kiwi comes off, the New Zealand comes off second. So that would be the moa and the kiwi. And last, the remnants of South America and Australia are joined together. So that would be those three. That's what you would expect if continents had done it. This is the actual genetic tree, which shows it's completely mixed up. There's no relationship between how these birds have got around the world and how the continents separated. So clearly they're flying, which changes our traditional view, and the ratites have often been a poster child for the continental movement. Now, what was more important perhaps is that the elephant bird DNA enabled us to estimate when this happened, when the ratites flew around the world. And it looks to be about 50 to 70 million years ago. Now that's a really big clue. because it's right after the extinction of the dinosaurs. That's when the dinosaurs go out there. That's the big meteorite impact. And when the dinosaurs go, there's a window of time right thereafter when the mammals are still these small insectivorous nocturnal things like rats running around the trees. That's all they're doing. It takes them about 10 million years to get down on the ground to become big. And during that window of time, there's nobody eating all the vegetation, no big herbivores. And so what we think has happened is the ratites are flying around the world at that point, have seized that opportunity to become big herbivores, effectively. And in fact, in so doing, they've all converged to look the same. So even though they started as small flying birds about the size of a partridge, getting around the world, once they've landed in these different places, different continents, they then grew to eat more vegetation over time, evolved, and converged so spectacularly that when you look at them now, we've always thought of the ratites as being a large flightless form, slightly divergent from one another. But actually, each of them had completely independently come up with that idea. And that's why it's been so difficult to work out their history. They all look exactly the same, but they started with something completely different. Now, furthermore, we can also look at the fossil record. Well, two things about that. One, once the mammals do become big, about 50 million years ago, no bird can ever try that idea again, because it's just going to be eaten by a mammal. So that small window of opportunity was the only time birds could become large and flightless effectively, unless they're on an island, like a dodo or something. Now, the other thing is, if you look at the fossil record, around the world at that point, we find these small ratite-like birds, about the size of a hen, turning up in Europe, North America, South America. There's this little phase. And we think that is pretty close to what the original flying ratite looked like. That's what the kiwi, the moa, and everything else started out as. Here's a more artistic version. And this is from Germany. That's 50 million years ago in Germany. That's pretty much what we start out as. That scale is about the size of a hen, a small hen of that. And yet, from there, we've managed to evolve into this kind of thing in the space of 50 million years, not involving hanging around on continents. It also explains why the kiwi is small. All the other ratites have become giants. Why did the kiwi remain small? It's because when it flew into New Zealand sometime around 50 million years ago, the moa was already in place and had already taken the niche of the large herbivore. So the kiwi couldn't compete, it couldn't move into that area. They had to choose something else to do, and a small, an insectivore, eating insects, was the alternative way of life. And if you're going to eat insects, doing it at night is better, because the insects are out. And also, you remain small. So hence, when they turn up together, the kiwi got the raw deal. The last thing, why do kiwi eggs? Why are they so large compared to the size of the bird? The largest in birds or vertebrates, effectively. And the idea had been originally that the kiwi must have been big, like all the other ratites, and became small over time, but kept a large egg. We're saying it's exactly the opposite. All the other ratites have become big, the kiwi has stayed much closer to its original size. We think the egg is big, as a conservationist suggested in New Zealand, because it allows the young to develop to a very advanced stage, just using the energy supply in the egg. It can stay in the burrow and not come out for a week or so until it's already walking and relatively advanced. And the reason for that is that back before humans arrived in New Zealand, there were huge numbers of aerial predators. Birds dominated New Zealand. We had the giant eagle, we had the laughing owl at night, which we know ate kiwis, or juvenile kiwis. Basically, it was a pretty dangerous place, and effectively, by having a large egg, the kiwi chicks could be advanced to a stage at which, when they do come out of their burrow, they are able to not instantly be eaten by owls, presumably. So, using the DNA from this bone, all the way from the swamp in Madagascar, we've been able to solve this evolutionary mystery that's been bedeviling us for 150 years, and finally give an explanation about where the kiwi came from. Completely different from the moa, and flying, which is about as bizarre as you get. So that's all I've got to say, and more than happy to take any questions or clarify stuff that didn't come through particularly well.
How reliable is this ancient DNA? Because I imagine there's not much of it in the bone.
No, absolutely. So how reliable is the ancient DNA? It's incredibly difficult work, and we had the DNA from the specimen way back in '94, and I've tried it several times since. It was very, very difficult to get anything reliable out of. And we've had to wait until the last few years when genomics technology, the same techniques we're using to sequence human genomes, has advanced orders of magnitude. And we've been able to use techniques where we fish out the DNA that we're interested in from the total amount of DNA we extracted from the bone, because that's full of bacteria and fungus and a whole bunch of rubbish that we don't want. And by using techniques to concentrate just the stuff we're interested in, and then use genomics technology to sequence incredibly deeply, just sequence everything that moves in that extract, we got so many copies of the elephant bird DNA, about 30 times. So every base, we got about 30 different copies of that base, so, of the DNA strand, so that we were absolutely sure about the DNA sequence.
How much, how much of the DNA did we identify?
We got 16,000 base pairs, which is the complete genome of the mitochondria. This is the total amount of DNA we got out. But we got it in only little pieces of about 60, 70 base pairs long, which is tiny in terms of fragments. So all we did is get millions of these things that actually all overlapped to make the complete sequence. And again, it was only with this new genomics technology that we're able to get such high resolution from the tiny damaged bits that were left.
And what's the Latin name for the? Does it have a Latin name?
Aepyornis, in this case. Big bird. Yeah. One thing which is slightly interesting is that the elephant bird, of course, was named because it's an Arabic legend. It turns up in Sinbad the Sailor. It's the rock, the thing that carries off the elephants in Sinbad the Sailor, and that's because when the Arab traders turned up in Madagascar, the eggs of the elephant bird, which are still quite commonly available, were shown to them. And you find an egg this big, which is how big an elephant bird egg is. You can stand on it, actually, should you want to. They clearly worked out that a bird that big had to eat elephants, and hence that was where the name came from originally.
And how did Tapapa come out with the bone?
Question is how did Tapapa, sorry, I'll just move to the microphone, how did Tapapa actually get hold of these specimens? We've got 9 elephant bird bones in the collection. Unfortunately, their history is actually very poorly documented. We know that one of them has a year written on it, 1933, but we've searched our archives and there's no, so far we haven't found any record of them arriving. So I would assume on that basis that they've been here for decades, and some of our bones may have even arrived here in the 19th century. What was commonly done is, because there was a lot of moa bones found, and they were fantastic for trading, I would imagine that our elephant bird bones were received because we were able to trade the moa bones with museums overseas, so probably from Europe, probably from England. Because we don't seem to have the written documentation, one way of finding out is possibly using things like the writing. There's some quite distinctive writing written on the bones, so if we can trace whose handwriting it is, we might actually be able to solve that mystery. So there's still more things to find out about these bones.
How old are those bones?
They vary. I mean, the elephant bird, when sorry, how old are the bones is the question. They vary in age. The elephant bird is thought to go extinct over 1,000 years ago. The actual date's less well known than the moa because the record is a bit patchy. These bones are probably between 1,000, 3,000 years, something like that roughly, just using moa bones as a guide. And I would add that these are some of the best bones I've seen. As I say, I've searched museums all over the world, and it turned out that, ironically, the museum right next door had actually some of the best material. And that's presumably, I think, because the moa bones were currency. Everyone wanted a moa skeleton in the museum because it's so big. And so as a result, the museum collections include, good dodo bones, good, all the mystery material. And New Zealand museums have some amazing stuff. Last year, for example, we did the Falkland Islands wolf, which was another evolutionary mystery. And it turned up in the attic of Otago Museum. One of the only 8 specimens known in the world was found in the back part of an attic. Presumably, again, someone had traded it for a moa skeleton at some point. So in that regard, New Zealand Museum's got some quite amazing material.
So from the time that the technique developed, how long did it actually take you to help piece together the DNA?
So the question is how long from the point at which the technique developed did it take us to piece together the DNA? We actually move very quickly here. The technique we use a lot on ancient human material, Neanderthals and other groups, so we're able to apply the technique as soon as we figured we should try it on the elephant bird. So from beginning to end it took only, I think, about 9 months, 8 months, which, waiting 25 years is relatively short.
What's the current limit on ancient DNA?
So the question is, what's the current limit on ancient DNA? If it's deep frozen, places like Greenland or permafrost areas, there's a whole genome sequenced from a horse, I think last year, that is aged about 600,000 to 700,000 years old. We estimate 1 million years is probably about the top end of survival, even under deep frozen conditions. But the vast majority of the material is less than 100,000 years. While that means we can't do dinosaurs or anything like that, it does mean that there's a record right through periods of major climate changes, the last ice age, and mass warming and cooling events. So it's a very good way to study what we're likely to see in the near future as we start playing with global climate.
Does the elephant bird have any descendants in Madagascar still?
No, so the question is, does the elephant bird have any descendants still in Madagascar? It's unclear how many species there were, but they all were rapidly eaten, I think you could safely say, or their habitat was destroyed after humans turned up. Very similar story to the moa. You've got a Kentucky Fried Chicken on steroids wandering around and a whole bunch of people turning up. It's not a good mixture, and these things don't run particularly fast, fairly clearly. So yeah, they weren't going to last very long, sadly. It's an all too, working in ancient DNA, this story happens all over the world. Every really interesting animal that had evolved evolutionary peculiarities tends to be first to go when humans turn up.
I've got a question online. When is it expected that we'll be able to fully identify and describe the original flying rat-eye?
Well, yeah, so it's a good question. When will we be able to accurately describe the original flying rat-eye? I think actually working out that these fossils are a very close look at what rat-eye started out as, because there have been mysteries. There have been these small flying birds that everyone said, well, it looks kind of like a rat-eye, but we don't know what it is or why it's there. Now that we've said, okay, this is the period of time when the rat-eyes are flying around the world, it's after the dinosaurs have gone extinct, they start like that, they rapidly become large, that then is actually a pretty good window as to what the original rat-eye looked like. Where did it come from? Well, our best guess, actually, is probably Antarctica. Antarctica is quite a nice place to be until about 20 million years ago when it starts getting covered in ice. And it's a nothofagus, the beach dominated temperate rainforests. And if you look at where the rat-eyes are, all these areas, Antarctica is the bit right smack in the middle. And that's where we suspect the homeland of the original rat-eyes were. And so in other words, it's unlikely that a kiwi's flown to Madagascar, or an elephant bird, even less likely, has flown to New Zealand. I mean, they're opposite sides of the world. It's much more likely that you've had a source population in Antarctica which has flown independently to both. That's probably more likely. So if we had to guess where the kiwi came from straight away, while its closest relative is the elephant bird, it may well be that both have actually come from Antarctica.
Any further questions? Cool.
Thank you very much.
Thank you, Alan.